Worker failures. The master pings every worker periodically. If no response is received from a worker in a certain amount of time, the master marks the worker as failed. Any map task completed by the worker reset back to their initial idle state and therefore becomes eligible for scheduling it to another workers. Similarly, any map task or reduced task in progress on failed workers is also reset to idle and becomes eligible for rescheduling. Okay, so yeah, I think this is a standard failure detection protocol, right? So, not sure what the name is this of this is, but the master can just uh, ping your worker on health check or any sort of check, and it basically retrieve the um, retrieve what do I say? Retrieve the health check periodically, and if it does not receive the health check in some sort of manner in some particular format, basically we mark it as failed. Mhm. Any map task completed by the worker reset back to their initial idle state. I just don't understand this line. Any map task completed by the worker reset back to their initial idle state and therefore become eligible for scheduling it on other workers. Okay, so it's basically saying that whatever the map task that was being run on that particular worker, which basically failed, we map it to the idle state and then we take that particular map task again and throw it on other worker. Okay. Similarly, any map task or reduced task in the progress of failed work is also reset to idle and become eligible for rescheduling. Yeah, the same. Basically, the moment like we have the failed worker, any task that has been mapped to that particular worker or was in progress or failed, we basically mark it as idle again and it becomes eligible for rescheduling and we should reschedule it to the other worker. But the question is that any map task completed by the worker are reset back to their initial state idle and therefore become eligible for rescheduling to another workers. The question is even the map tasks which were completed by the worker, they also get marked as idle. If I have to guess, I'm not really sure, but if I have to guess, it's probably because like they don't want any kind of side effect, right? So the example is that let's just say map task was completed and then the worker was failed. So they just want to be sure that since we don't have any kind of side effect or some sort of long term issue because of this, they just said that okay, this task was never completed, just recomplete it again. So that will effectively ensure that whatever that has been done by that worker which was now failing, it will effectively act as a mechanism which will make sure that that worker never worked, and whatever the task that has been completed or was completed, it will be rescheduled to other workers which are working. I think I just want to make sure that this works as per we want, right? So thought about this. Let's just think. This paragraph describes this a very ideal system of MapReduce, master. Yeah. I understand. If no master, yeah. This is any map task completed by the worker reset. This is the important part. In system like MapReduce, map tasks produce intermediate data. That intermediate data is stored locally on the worker's disk. Ah, I'm so dumb. I'm so dumb. Yeah, that makes sense. Yeah, that makes sense. Okay, not here. That makes so much sense. Yeah. Basically, like we have the worker. Once that worker completes its work, it flushes the data out to its local drive, right? And then that local drive is used by the worker used by the worker from the reduced task. Worker work. I don't know, like reduced task worker do RPC on that particular map worker to fetch the local flushed intermediate keys, right? Now the point is like if this is not available, right? So since we have flushed since all the tasks that has been completed by this map worker and the result that has been flushed to its local drive, it will also be basically unavailable, right? So in that case, it wouldn't make sense for us to do RPC on it and try to retrieve it from a non-working worker. So we are just going to make sure that all the tasks that are completed by this worker, they never just like we just going to reset back it to idle stage and propagate it to the other idle workers. Mhm. Since now they will be completed, they will be written or flushed out to a local drive, but this time since that is a worker which is working, the RPC or the remote read will be working correctly. Okay, so this is that local data is gone, so the system must redo that work. Even completed tasks on that worker treat as they never had. They go back to yeah. Mhm. Yeah, okay. So basically, it was such an easy thing I just missed. Completed map tasks are re-executed on failure because their output is stored. I'm so dumb, but literally the answer was written in the next line. I was literally just trying to, I don't know, like hypothesize why they are actually uh, trying to reset the trying to reset the work that has been completed by the worker. I was trying to hypothesize, I was trying to predict their reason, but like it's literally written in the next line. I just had to scroll down a bit. Completed map tasks are re-executed on failure because their output is stored on the local disk of the failed machine and is therefore inaccessible. Yeah. Completed reduced tasks do not need to be re-executed since their output is stored in global file system. Completed reduced tasks. Yeah, yeah, yeah. Makes sense. Because like once we have the output, like once we have a reduced output from the reduce worker, they are written to a output file which is basically globally accessible. The reason being because now it's need to be passed to some other distributed algorithm or maybe even to some other MapReduce invocation. So yeah, it's good to be just globally accessible. Mhm. But not this because like it's going to be only internally used by reduce worker. So instead of uh, wasting your time and energy on making it globally accessible, we can just do a RPC call since they are in the same network. When a map when a map task is executed first by worker A and then executed by worker B because worker A failed, all workers executing reduced tasks. They are talking about map task, right? Okay. All worker executing reduced tasks are notified of the execution. Any reduced tasks that are not already read that are that has not already read the data from worker A will read the data from worker B. Yeah, so that's what I was going to ask. That let's just say worker A, let's just say this is the worker A, it writes the data on its local disk and now it's basically not working. So there's a little small chance that what could have happened is that worker B, my worker B worker B might have read some data from here, but since we are going to do the re-execution, we need to. Okay, yeah, just okay. Yeah, so I think I understand. So basically, once we have appended data here, obviously there's a small step where master is notified that hey, this is the location, and please notify the reduce workers about this location. So the master would have told about the location of this local disk to different reduce workers. But since now this map worker is down, basically this location is not accessible and we are going to re do the work again. Basically this means that we have to tell the tell the reduce worker that the location that you have been once notified in the past is now non-accessible, and this is now switched to this because of the issue. So basically, once we switch because of the failure, we have to ensure that our reduce worker also knows that same stuff. But one thing I did not understand and I'm still trying to comprehend is that, does reduce workers start working once they have, let's just say, some sort of data or intermediate key available, or like they first wait for all the map workers to finish working, and then once all the map workers have flushed their data, only then they start working? So like, I can give a situation where, let's just say, worker A completes its thing, and it writes out the it flushes out the data, and B and C are still not completed. So does that mean that reduce worker, this one, can pull the data from here and start working, or it has to wait for all of the data to be completed, all of the intermediate keys to be flushed out, and then it will pick it and then work on it? Well, well, technically, for the best case scenario, it would be easier just to wait for the whole data to be flushed out, and then reduce workers can pick the data. The reason being, let's just say we have some key, let's just say we have key A here, and then we have key A here as well. Yeah, we have key A here, we have key A here, and if they wait, then we know that whatever the partitioning function has been written, let's just say the hash one, the hash of the key will be the same, so they will be, no, 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 yeah, okay, 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 yeah, it won't matter. I thought that once they have been written here, only then the partition function will kick in, and it will then transfer the keys to this worker. But that does not matter because partitioning works for this stage only. So this means that we have written it whatever we have written in the worker, it gets flushes out to this particular to this particular local disk, and then it's partitioned accordingly. But okay, wait, it makes I'm getting confused now. Okay, so each worker have its own local disk. This means that we have different local disks containing different set of data. This means that like, how is the partitioning going to work exactly here? Because we already have some sort of partition data, like partition based on the disk of that particular worker. So let's just say this is the local drive of this worker, this is the local drive of this worker, this is the local drive of this worker. It is already partition data, right, in some way, based on the worker disk. So how are we going to exactly partition it? Okay, and then we have like, okay, that's one question. So where the partitioning comes in, and then we have like the other question which I asked initially, that when will the reduced worker will start working? As soon as they get some data uh, from a partition data set, or after all of the map workers are finished? Okay, these are the two questions I need to write. Answer: we have some questions we want to confirm. As per this map reduce paper. Okay, also let me just give it the link. I know that it probably does not require the link, but yeah, it's easy for me to understand and to tell that I am using this particular paper as reference. So the first question is that mm, okay, I need to I need to again think like what was the question. Okay, so the intermediate keys are that are produced by, I don't know, map workers are flushed to their local drive. Correct? If that's the case, this means that we will have multiple, okay, excuse my bad typing, multiple map workers having different key intermediate key values produced and stored in their own local drives. Now, MapReduce paper says that the reduce worker picks the intermediate key value from the partition data that is created using the user provided partition algorithm. But where will that partition algorithm work, as we already have the data partitioned by the local drives of the map workers? There is no necessity to partition the data once again. Though we need to partition the data, as we need to group the same/similar keys together, but that partitioning can be done how? Let's see. Okay, that was so much bad English and typing. Anyway, like, I just want to get it done right. It will probably understand all the thing I said. So great question. You are thinking exactly in the right details. Okay. Classic GPT encouraging us. Are intermediate key value flushed to the map worker's local disk here? The original MapReduce paper described the same. Each worker processes input split, produces intermediate key value pair, buffers them in memory, periodically writes them into own local disk. So this is exactly what the paper describes. So yes, intermediate data is written directly to the local disk of the map machine running the map task. Okay. Does that mean the map multiple workers store? Does that mean multiple map? Let me just increase this again. Does that mean multiple map workers store different intermediate data locally? Yeah. Handle different chunk of input, produces their own intermediate key value pair, store them locally. So after all map function finish the task, the intermediate data is to spread across many machines, stored locally on each machine that ran a map task. Makes sense. Where does this partitioning algorithm run? This is the confusion. And here's the important part. Partitioning happens inside the map worker before writing to disk. Okay. It does not happen later at the reduce side. How partitioning actually works. Suppose there are m map tasks are reduced tasks. Each map worker produces intermediate key value pairs. For each key applies the user defined partition function. So inside the map worker, it divides its output into R partition. Each partition corresponds to one reduce worker. The map worker writes R separate file into local disk, one per file. Yeah, that makes sense. So if you have 3 reduced tasks, each map worker creates 3 intermediate files. What does the reduce worker do? Now comes the shuffle phase. Each reduce worker is responsible for partition number, say partition 2, contact every map worker, fetches only the file corresponding to the partition 2. So the reduce worker 2 collects partition 2 from map 1, partition 2 from map 2, partition 3, 2 from map 3 from all map workers. Why is the partition still necessary? We already have the data partition by the local drive of the map worker. Not quite. The local disk partitioning is by machine, not by key. Makes sense. The partition is needed so that all identical keys go to the same reduce worker. Without the partitioning keys, the same key could end up in multiple reduce workers. That would break the correctness. The partition key guarantees same key, same reduce. Yeah, okay, that's a good thing. So we also implicitly confirm that we have to have partitioning function that guarantees that same key get mapped to the same reduce worker, right? Because if we have same key goes into different functions or different workers, that will essentially lead to a bad algorithm, partitioning algorithm, which will basically should not be used in MapReduce. Okay. Yeah, okay, that also makes sense because literally all the arrows, because each of the worker arrows pointing to each of the local disk arrows are pointing to both the worker. This means that each of the worker is actually going to read from all the local disk of map workers, and then we have two partition here. Okay, then next comes the next question. Okay, another question. Does the reduce Yeah, okay, that essentially answers the question. The next question was whether the worker will work once it have some sort of data to work on. Let's just say this worker is completed. So we have this this local disk completed with all the data required, but these two are still in progress. So the question was whether the worker will take this and start working, or it will wait for this. It will wait for this. In fact, it had to wait for this because it needs to go to all of the map worker local drive and pull out the partition data that it wants. So if it starts working when both of these are in progress, it will basically not have all the data. So it has to wait for the map workers to be completely finished. Then again, let's just ask for the sake of completion. Does the reduce function can start working even if not all the map workers are finished working? Maybe some are in progress and some completed. So can reduce function start working with the completed ones, or it have to wait till all the map workers are finished working? This question to the important detail. Reduce function can start. Okay, it can start. It can start before all map tasks finish, but it cannot finish until all map are done. Mhm. So I understand basically what is going to be. It's going to say that okay, hey, it can start. Let's just say this is completed. These two are not completed. So it will say, hey, it can start. The worker can pull the data in, start working on it, but it won't be finished until unless it's also pull the data from these two. it can basically prefetch the data before the whole process of these things. It can basically prefetch the data, work on it, but it also have to be take this, and only then it can finish the task. In the original MapReduce design, reduced tasks are scheduled early. They do not wait for all map to complete. So yes, reduced tasks can start while some map are finished, some map are still running. What can the reduce workers do early? The reduce execution has three phases. Okay, so I did not know about this. Phase 1, shuffle, copy phase. Start fetching intermediate partition, pull data from map worker that already finished. Continuous pulling unmapped workers, makes sense. So it can start copying data immediately. Yeah, okay. Then as the data arrives, the reduce worker merges and sorted by key. This can also begin before all maps are done. Yeah, okay. Reduce function execution. This is important part. The actual reduce function for a key cannot run until the reduce worker has received all the data from that partition. That means all map must complete because any map task might still produce values for a key. If we reduce too early, we might miss some value. The reduce worker waits until all maps are finished before final reduction completes. This overlapping improves performance. Blah blah blah. Okay, yeah. So that answers the question as well. So they are basically doing the performance improvisation by prefetching the data before the whole process is completed. hmm Makes sense. Makes sense. hmm The map, okay, now let's just move on. The map reduces resilience to a large scale worker failure. For example, during one, yeah, that was going to be the next question, not directly, but once I've read the line, I understood. So let's just say we have 100 data, and since we have 100 workers, if one worker failed, we know that we are going to delegate its work to the 99 workers. The master is going to do that. If two fails, we are going to take those two work and delegate it to the remaining 97, and that's how we are going to do. But what if almost all of them fail? Let's just say 97 fails and 98 fails. Like remaining 1 2 nodes has to all of the work from the 97 98 node will be delegated to the remaining two nodes. Though it will work, it will just be a lot of time consumption and it will be a lot of load on two nodes. So how they are going to mitigate that? For example, during one MapReduce operation, network maintenance on a running cluster was causing groups of 80 machines at a time to become unreachable for several minutes. The MapReduce master simply re-executed the work done by the unreachable machines and continued to make forward process, eventually completing the MapReduce operation. Okay, so it says that just don't do anything, like there's nothing like horizontal scaling. If they fail, they fail. We are going to execute the work on the remaining workers, and that's it. Like, don't care. Like, if it takes load, takes load. We can't do much. Yeah, that's also a viable strategy. hmm I'm saying viable strategy like I know how to actually solve this in much better manner. I think that's probably a much better and more simpler answer because it makes sense that hey, I can't do it. Like, we can't do much. We are not going to add nodes because a lot of the nodes just failed. Also, not to mention that since it was an internal Google network, the chances of the chances of uh, a very high count of nodes failing at the same time is pretty low. And even if they fail, they should be back up in some other time if it was some intermittent network issue. So yeah, they probably did not want to invest that much time into solving this kind of edge case. And it's not like this edge case is a blocker, right? It does not block the process. It just makes it a little slower. Mhm. If the constraint would have been something else, maybe they might have solved it for better uh, speed, but I guess they are not going to. Okay, so we now know that the nodes are dependent on master, right? Because master is the one when a node fails, master say that hey, this node fails. All of the tasks that have been completed or are in ideal state or whatever it is, like in progress, it reset back them to idle and then reschedule it to the different workers. This means there is a single point of failure, master, right? So classic problem arises like what would happen if master failures. So without even reading this, I can guess one thing, that if master fails, they probably need, if leader fails, they probably need to actually make other node a leader, right? So I think I read it in DDIA that uh, we can have like once the leader fails, we can have another leader promotes another node, or another slave node promotes itself to leader, and that there is multiple algorithm to do that. So I know one algorithm for it, right? But I just don't remember it top of my head. So yeah, I think that's a good viable strategy that we can do. Let's see what they did. It is easy to make the master write periodic checkpoints of the master data structure described above. Okay, if the master task dies, a new copy can be started from the last checkpoint state. Yeah. However, given that there is only one single master, its failure is unlikely. Okay, therefore our current implementation aborts the, oh, that's interesting. So I thought they will probably promote till this point. They said that okay, we check, basically what this line basically means, from what I understand, is that master basically periodically saves its state to the master data structure, right? So it saves it in some time, and if it fails, like we can always use the last copy we have of the master data structure uh, to start the whole process, right? So I thought that maybe new leader will come in and it will pull the configuration from the master data structure and get started, right? We can obviously see like what are the differences that has been uh, missed, or maybe like orphaned after the configuration was saved for the last time and before the master dies. But yeah, that's another talk. But I thought that that's how they are going to do it. But they literally just abort the implementation. They said that for their infra, it's highly unlikely that single master will fail. So if it fails, we just abort the process. Which, now that I think about it in hindsight, is really smart, because it reduces all the complexity of leader promotion and all the other stuff. Like, and therefore, a current implementation aborts the MapReduce competition if the master fails. Not to mention, it's based on their own infra. So if they're pretty sure that okay, it's very highly unlikely that single master will fail, so why invest time in something that is a really, really rare edge case for them? And that's a good point. So this means the knowledge I had from DDIA is pretty useless here, because I need to understand the constraint on which this research paper is working. So right, I just can't just take the general information I had. Like I know that leader promotion is a thing. We just can't do it in this case. We can do it in this case. We just don't have to do it in this case. So that's something we have to understand, that distributed problem is not something I just put random fancy algorithms I know into place, general algorithms into place, but rather it's something I have to ask the constraint about. So I had to ask one thing, right? What is the chances of it will failing in this case? And if it fails, what if we just don't do anything? What if we let things error out? Will that make things too hard? And that would probably answer the question, because they don't think it will make things too hard. If it fails, just restart the whole process again from zero. Just wipe everything out, make a clean slate, and restart the process. Good point. Client can check for this condition and retry the MapReduce operation if they desire. Yeah. That's a good. I'm, actually, the more I think about it, the more it seems smarter, right? Like, to me, this like really is a good actual design, because they did not want to invest time in something that is actually already solved. I'm not sure whether it was solved in 2004, but it obviously the Google engineer had ideas about the leader promotion and all the other stuff, right? They just designed it very purposely that they don't want to figure that out. And to me, that's really smart. I'm actually pretty dang impressed with this decision. Semantics in the presence of the failure. When the user supplied map and reduce operation are deterministic function of the input values, our distributed implementation produces the same output value as would have been produced by non-faulting sequential execution of the entire program. I mean, this is, even if it's hard vocabulary English, it's pretty easy to understand. What they mean to say is that if map and reduce functions that have been provided by the user are deterministic, meaning they are only dependent on the input, and as long as we have the same input, no matter how many time we run the map or reduce function on those input, it will always and always produce the same output. This means that if they build if they build a system where if they build a system where they do the parallelization and all this stuff, and they build it correctly, so this means that all the distributed stuff they did, all the parallelization did, will result in similar output if they would have done it sequentially. That's what they mean. We rely on atomic commits of map and reduce task output to achieve this property. Yeah, that makes sense. Like, we need to have, like I said, there's no dependency of map and reduce and their input keys or values, uh, interdependency among different keys and values and their map function or reduce function. Okay, there's some dependency of reduce, I guess, but map function, there's no dependency, right? So it's pretty atomic, so they can just parallelize it. Each in progress task writes its output to private temporary file. A reduced task produces one such file. A map task produces r such files, one per reduced task. When a map task completes, the worker sends a message to the master and includes the name of the r temporary file in the message. If the master receives a completion message for an already completed map task, it ignores the message. Otherwise, it records the name of the R files in a master data structure. Like, so, if like it's the thing that we are now understanding, right? So the question I asked previously GPT was this, like, this very bad English question, that how is the data partitioned? So they are telling it. So anyways, the point being that map completes and it messages the master that hey, this is completed. I wrote the message. Now you can send the location to the worker, and yeah, master takes in registered information into the master data structure, and we move on. But there's one point I would like to actually emphasize. If the master receives a completion message for an already completed map, it ignores the message, right? So the thing is, one might ask, like, why even we are having multiple messages, right? So let's just say once the worker completes, it sends the message to master, and hey, that's it. Like, why we have to send it again? The reason being, there might be some sort of mechanism that is ensuring that in case there's some issue that uh, yeah, so the issue is like, let's just say master fails. Since we are not uh, sure whether master failed or not, because we have not, the workers don't have much information about it. uh, there's two things we can do, right? We can send the single, we can send the message single time and forget about it. So let's imagine a situation where the master was down for a single instant, and in that instant we send, the worker send that message. This means that the master would not have picked that message up, and that message would be gone. Now the master does not have any information, and the worker is thinking that, hey, I have sent it, my thing is completed, now master will take care of it. But since master was down for an instant, it does not know about that particular worker. So basically this is a situation where workers think that, hey, I am done, and I have sent the data, master will take care of it, but master does not know about that data because it was down for a second. So this is, I think, uh, this is also, I think, a concept in PubSub, which says that like, so the point is, mm, that one of the easy solution is for to resolve this is to, for worker to send it multiple times. So send it multiple times. If it was even, I don't know, uh, if master was even down for some time, and did not pick the initial messages of the worker, when the worker periodically send the message, the master, when the master will be available, it will pick the message up and it should be good to go. Now you might be asking, hey, what if we already sent the message, master picked it up, now we send it again? Like this line says that it is going to ignore the message. That's one thing. So I think, yeah, looping back to what I was saying about PubSub, okay, you know, before going to PubSub, I just want to beg the merchant sorry. But the thing is, like, I had the thought here of this whole thing, right? But I speak so fast that I'm not sure how the thing came up, and I'm pretty dang feeling bad about it. So then again, this is the learning. Go a little slower, even if I know stuff. So yeah, looping back to PubSub. Basically, in PubSub, publisher can publish a message, right? So there's couple strategy behind it. One of the strategy is uh, single emission. I'm not sure about the name. Basically, it's fire and forget, right? So we fire the message and we forget about it. The resilience mechanism will be taken care. Like, we don't care about the resilience mechanism, but the publisher will just publish it once and it will be happy. So it's fire the message once exactly. So it's exactly once. So yeah, this. So if we don't, yeah. So that's the issue, right? If the subscriber in that publisher subscriber design is, if the subscriber is down, this fire the message once and forget can lead to some issue, right? So for this, like I said, we have other strategies like fire at least once. So we are going to fire like couple of times, right? Now you might be saying that, how, in which periodic manner we are going to fire? We can fire it in some periodic manner, or we can fire it using the exponential droplet. We are going to exponentially increase the time frame between each periodic, not each periodic, between each fire. I'm not sure how that came up, but I hope you get my point. Anyways, when a reduce task completes, the reduce worker automatically renames its temporary output file to a final output file. Mhm. If the same reduce task is executed on multiple machines, multiple rename calls will be executed for the same output file. Wait, what? If the same reduce task is executed on multiple machines, multiple rename call will be executed for the same final output file. We rely on the atomic rename operation provided by the underlying file system to guarantee that the final system state contains just the data produced by the one execution of the reduced task. I did not get it. If the same reduced task is executed on multiple systems and multiple rename calls will be executed for the same output file. Okay, I guess that makes sense. We rely on the atomic rename operation provided by the underlying file system to guarantee that the file system state contains just the data produced by one execution of the round task, reduced task. Okay, so I think what they basically mean to say is that map, like we know that reduce will temporarily flush out the data as well. Like map temporarily flush out the data, and once it's complete, it sends the message to the master saying that hey, it's completed. The same is going to be done in reduced task, but once the temporary writing to the local disk is completed, what we are going to do, we are going to rename the final output file since it's a global shared file, right? I think that's very easy to understand. They have written all sort of things like if the same reduced task works on multiple machine, multiple renaming is going to be called. That's pretty self-explanatory. They also rely on the atomic rename operation so that we don't have some sort of race condition arising because of it. So yeah, but on and all, basically they are saying that reduce function writes temporary output file, and once it's completed, it's renamed to a final output file. That's it. Atomically, obviously, so that we don't have race condition. The vast majority of our map and reduce function are deterministic, and the fact that our semantics are equivalent to sequential execution in this case makes it very easy for programmers to reason about their program behavior. Yeah. So since everything is predictable, atomic, and deterministic, like user can think of it in a similar mental model as they would have thought that it's a sequential thing. They can think that it's a sequential thing and they can write and program as per sequential logic. But since the nature of the map reduce abstraction, the abstraction will automatically parallelize it so that the programmer will get the performance of parallelization but a mental model of sequential, which is pretty easy to work around with. Mhm. When the map and or reduce operation are non-deterministic, we provide weaker but still reasonable semantics. In presence of non-deterministic operators, the output of particular reduce function R1 is equivalent to the output of for R1 produced by single execution, a sequential execution of the non-deterministic program. Okay. Aside, like this paragraph itself says that when when the logic is deterministic, when the map and reduce is deterministic, is pretty easy, right? We already thought about that. But what if it's non-deterministic? Then the map reduce abstraction will still be somewhat reasonable, but it has weaker semantics and weaker uh, reasonability to work around with. So they said that if we have non-deterministic, easy. If we have non-deterministic operators, uh, let's just say the output of R1. So if they have non-deterministic operator, this means that the output of R1 reduce R1 task is going to be equivalent of R1 task if it would have been done sequentially with obviously the non-deterministic program. Obviously, since if we are going to talk about R2, a different reduced task, it could correspond to different output because the sequential execution, because of the different sequential execution of the non-deterministic program. Okay. So the logic is that since if it's a non-deterministic function, it could vary because of a lot of side effects. So one of the reduced tasks R1 could be different from other two R2, right? So the weaker semantics that MapReduce provides that it says that hey, for the R1 with non-deterministic output is still going to be equivalent to sequential execution of the non-deterministic program. But for R2, it is still the same, that it will still be the sequential execution of R2 of non-deterministic program, but R1 and R2 will and could not be same. Okay, consider map task M and reduce task R1 and R2. Let's EI be the execution of RI that is committed there. I'm tired. Okay, anyways, consider a map task M and a reduce task R1 and R2. Let EI be the execution of RI that's committed. There is exactly one such execution. The weaker semantics arise because ERI may have read the output produced by the execution of M, and ER2 may have read the output produced by a different execution of M. Okay. So in simple words, it's saying that what could happen is that one execution of reduce, let's just say R1, of of the execution of R1 could have read a map task and produces output accordingly. Now let's just say we have another R2 reduced task 2. Its execution could read the output of M, which is basically map task. Read the output produced by different execution of M. Wait, I have to understand this. Like I think I understand it, but it's not easy for me to explain, so I will probably give it to GPT to once confirm it. Okay. We have map task M produces some intermediate data, reduce one consumes the M data. Okay. Map task reduce task can be retried if the worker fails. The execution of R1 that eventually commits successfully. The weaker semantics arise because ER1 may have read the output one execution produced by one execution of M, and E may too have read the output produced by different execution of M. The map task M might run multiple times if there is a failure. So original execution M1, the execution M2. The reduced task R1 might pull intermediate data from M1. Reduced task R2 might pull intermediate data from M2. Even though R1 and R2 both see the data from M, they might not see the AM execution of M. The MapReduce does not guarantee strict consistency across reduced tasks during intermediate stage. The final output is still correct as long as every reduced task uses committed map output. But at the granular execution level, different reduce may read data from different retries of map. Strong semantics equal to all reduce sees output from same execution of different map tasks. Reduce may see each output from different Map reduce relies on item potency. Map map task reduces the same intermediate output no matter how many times they run. Reduce tasks only commit once after fetching all the data. So even if R1 reads from M2 and R2 reads, the final output is logically consistent as long as only committed map output are used. Reduced tasks safely retry without duplication. Okay, I'm still not sure. Not gonna lie. I'm still not sure. I'm still not sure. I have to probably give it like this. Yeah, I have to give it like this. There's just no other way. There's just no other way. Explain in short. I don't want to read like 1000 lines. MapReduce assumes deterministic operator. Yeah. But if MapReduce are non-deterministic, yeah. Each reduced task task. Each reduced task final output correspond to some valid sequential execution of the program. Different reduced tasks R1 and R2 might see different output from different execution of the same task if map was retried. Yeah, so they are talking about the retried only, retry mechanism of map. I did not guess that. So weaker semantic just means that different reduced tasks may use intermediate data from different runs of map tasks, but each reduced task output is still internally consistent. The final job is still reasonable and valid even if it's not fully deterministic across all reduced tasks. Okay, now I think I understand it. So basically, point being, let's for now let take the deterministic thing. So if map and reduce are deterministic, no matter how many times we retry the map task, it will give the same result because that's the nature of deterministic algorithm, right? Give the same input, it will produce the same output no matter how many times you rerun it. But what about its non-deterministic counterpart? If we have retries in map task, this means that non-deterministic can give multiple answers, multiple different answers based on the execution of them. Yep, because of some side effect or something else, right? Then obviously it could give the same answer, but it could also give the different answer. So we are going to take the worst case. Now, for non-deterministic, if m on different retries give different result, our task, let's just say we take two reduced tasks. One picks up the first retry, when one picks up the first execution of map, and R2 picks up the second execution of map, which is basically M2. It could obviously it will still result in the same output in the overall long run, but E of R2, basically execution of R2, E of R2, yeah, basically E of R2 could produce different result from E of R1. Obviously, uh, when the whole machine is considered, it will still give the same output. But yeah, I think that's the logic. That's the weaker semantics they are talking about. That if we have inconsistencies or non-deterministic program, each of the smaller runs, each of the smaller execution or the task runs can produce different output uh, among different retries or among each other. But when considered the whole system, they can and they will produce the same output. Obviously, none of this applies to deterministic function because deterministic itself correspond to the fact that as long as the input is same, no matter how much time we retry the function, it will still result the same. But for non-deterministic, it's different. So basically internal state could be different with each retry or among each other, each execution run. There could be small differences, but the overall machine output should be same. Okay, I think that makes sense. I mean, still a little bit confusing. I'm not going to lie, but I think yeah, that's covered it up. I think yeah. Okay, I still have like a lot of things to work, but I think yeah, that's it for today's video. Still, it was interesting. To me, the most interesting part were three things. Not three, but like a couple of things I would like to mention. First of all, there are different implementation. There could be different implementation for each MapReduce. That's one thing I wanted to ask, right? I wanted to emphasize. Then the second is like how this whole diagram works, like the partitioning. Like partitioning, I did not knew that there could be partitioning, which was really cool. And the third part, which you probably might have guessed, where it is like master failure. So the fact that they are not handling master failure because it's very unlikely to happen is really good. So yeah, I think that sums it up. Okay, it was a lot to take in. It was a good read.